Welcome. In this video lesson, we're going to take a look at a qualitative analysis involving finding equilibrium points, generating phase lines, and discussing bifurcations. So, an important model analysis that we often like to conduct is called an equilibrium analysis. And an equilibrium analysis is an analysis involving equilibrium points, which is any value of the dependent variable y equals some value that makes dy dt equal to 0. So if you think about in context what this means, if dy dt is 0, then that indicates that there is no change in the dependent variable. So basically we are in an equilibrium state. So if you have a population in which dy dt equals 0, and we should say that this is the case for all t, that is for all time, it's a value of the dependent variable that makes the rate of change 0. We then describe what happens to dy dt for y below that value and for y above that value. So if there are multiple equilibrium points, then we basically do what you might think of as the first derivative test, where you look at all the values or all the intervals surrounding the critical points, which is what these are. They're critical points. And you look at the sign of dy dt is the function increasing, decreasing, or constant. And this is called a qualitative analysis because it describes the characteristics of a solution function. We're not actually really solving the differential equation itself. In some cases you can't. In some cases you just want to conduct this quick analysis to gain more insight about your solution. So here's a problem we looked at in the previous lesson. Suppose you take out a loan at 1% per month. You make monthly payments of P equals $100. Conduct an equilibrium analysis for this model, which when P was 100, we had 0.01y. That's the interest component, the inflow of money increasing your balance, but then you're taking away $100 from that balance. You're basically paying it off. So to conduct this equilibrium analysis, we want to find the values of the dependent variable. In this case, that dependent variable is called y, such that dy dt equals 0. So what we want to solve is, we want to solve this equation here, 0 equals 0.01y minus 100. And then if we rearrange this simple equation now, and we add 100 to both sides and divide by 0.01, we get y is equal to 10,000, or y is equal to 10,000. Now, if we look at y equals 10,000, what's happening here is we're basically saying that when y is 10,000, in other words, your balance in this account is $10,000, you take out a $10,000 loan, and you make $100 payments, your balance is not going to change at all. We found out now that $10,000 is 1% of 10,000 is 100. So in this term here, we're adding basically 1% of $10,000 to your balance, and 1% of 10,000 is 100. So you're being charged $100 in interest, but you're making a $100 payment, and so your balance will never change. Now, if we kind of do a first derivative style test, and we draw a number line here, and we say that this is really the y-axis, and that when y is $10,000, we are in equilibrium. That is, the balance is not changing. But what happens if y is just slightly bigger than 10,000? So if we pick a value to the right of 10,000, for example, at y equals 11,000, and we plug that into this equation to see what is the sign of dy dt, we get 0.01 times 11,000 minus 100, and that is going to come out to a positive 10. And so what that means is really we don't care about the 10, we just care about the fact that the sign is positive. And so that means that dy dt is bigger than 0 for all values to the right of y equals 10,000. And we can do the same thing at a value less than 10,000. Now the reason that we only need to check one particular input into this function on each interval is because the only way for a different derivative to change signs is to pass a critical point or to pass some sort of break in the graph like an asymptote. This function and most of our functions are defined for all y and t, and so it's not really a problem. But if we pick something like y equals 9,000, then we're actually going to get dy dt is negative 10. And so the fact that is negative is what's important over here, and that means that off to this interval, dy dt is less than 0. So what does that mean? Well, that means that if you take out a loan of $10,000, you'll never pay it off. If you take out a loan bigger than $10,000, well, now your balance is going up. If you took out a balance of $11,000, then your balance would actually go up by $10 per month. So here, your balance is growing, and you'll never pay off the loan. And here, the balance is decreasing, so you will pay off that loan. In other words, you shouldn't, if you want to make a $100 payment and you're being charged 1% per month in interest, you would not want to take out a loan of anything near $10,000. Now, you don't get to choose your payment, but just for the sake of argument, we're making this discussion. Let's take a look at another one. This is also something that we took a look at, and we did find out that P equals 100 was basically the biggest payment you could make for a loan that we classified as being a $10,000 loan. So notice that this quick little analysis here gave us the same level of insight that having to solve this entire model by using separation of variables did. Now, we got the gist of things here when we actually solved it. We had a function to plot. We don't have a function to plot here, but we were able to make some pretty powerful conclusions. So this is a model where we said, suppose 30 grams of a toxic substance enters a 10,000-gallon pond each minute through waste runoff from a chemical company. To keep the water level constant in the pond, water leaves the pond through a stream at 20 gallons per minute. We found in a previous lesson that dy dt equals 300 minus 0.002y. Conduct an equilibrium analysis. All right, so once again, we'll set this thing equal to 0, and we'll solve. And so this is just a two-step equation. So we want to do 300 divided by 0.002. Now it looks like I have an extra 0 here. There should be 30 minus 0.002. And this, when we solve this equation, we get 15,000. Now that's a number that we recognize as being a pretty important number in our previous problem. So let's see what's going on here. If again I draw a number line here, I say that these are the values of y that get inserted into here, then I have an equilibrium point here at y equals 15,000. And I want to know, okay, so if I ever have y equals 15,000, in other words, if the pond ever ends up having 15,000 grams of this toxic substance, then it's at a saturation point. There will be, over time, no additional change in the amount of the toxin inside the pond. Now, some will be entering, right? Here's our pond. We have some entering and we have some of the substance leaving, but the mixture in here, if it ever achieves 15,000 or starts at 15,000, there will be no change in the amount of that toxic substance in there. But if we look at a value that is bigger than 15,000, let's say 16,000, and we look at dy dt, if dy dt is 16,000, then we're actually going to end up getting, and you can verify this by plugging it in, a negative value. I'm not even going to worry about the value, the numerical value that I get, because I just care to see that dy dt is less than 0. If we look at another value such that this value is less than the 15,000, say y equals 14,000, then we're going to get dy dt is positive. Okay, so that means that here dy dt is bigger than 0. So if we actually put some arrows on this number line to indicate a little more clearly what's going on, we could say that in this case, because dy dt is positive, well, that means that y is increasing. And if y is increasing, that means it's getting closer to 15,000, which made sense because our initial concentration was 0 inside of the pond, and we saw that over time, what happened is the value of y, if we looked at the y versus t graph for having initially 0, we saw something that looked like this with an asymptote here at y equals 15,000. Notice that we don't have any information here about t. We're not really concerned about it because the qualitative analysis just tells us what's happening. And here if dy dt is less than 0, that means y is going to decrease, and it's going to decrease closer to y equals 15,000. Again, if it hits 15,000, the amount of toxic substance in that pond, then the rate of change becomes 0, and we are basically at a saturation level.